Okay, and welcome back. All right, so in this section, we're going to start talking about joint probability distributions. And before we go ahead and do the definitions for these, I want to just kind of look at an example to get things going, because I think the definitions, again, depending on how familiar you are with some of the notation, can look kind of complex. And I think if we have a rough understanding of what a joint probability distribution actually is, it makes the definition a little bit less intimidating. So let's say that we're going to flip a fair coin twice. Going to go ahead and let x be the number of heads. So capital X is going to count the number of heads that we get. So we have a single fair coin. We're going to flip it twice. And I'm going to define another random variable, y. I'm going to say y is equal to 1 if the first toss is a head. If the first toss is a head. So y is really just keeping track of the first toss here. Y is going to equal 0 if not. First toss is not a head. All right, and so let's take a look at what we can have here, okay? X can be what? X can take on, well, if you flip a fair coin twice, it's possible to get 0 heads, 1, or 2 heads. And Y can be just 0 or 1 because it's only keeping track of the number of heads that we get in the first toss, okay? So what I'm going to do is I'm going to look at some probabilities of both X and Y combinations, some intersections, if you will, right? This is sort of like probability that X equals 0 and Y equals 1, but we're talking about random variables here, so we tend to just use a comma. So what's the probability that X is equal to 0 and Y is equal to 1? Well, if X is 0, X is counting the number of heads we get. Y is supposed to equal 1 if the first toss is a head. Well, if the first toss is a head, but there are no heads, that's contradictory. That can happen. So there's a 0% chance there. That intersection is empty. That intersection is empty. So the probability that happens is 0. What about the probability that X is equal to 0 and Y is equal to 0? If X is equal to 0 and Y is equal to 0, how likely is that to have happen? Well, if X is 0, that means we get 0 heads in the first, we don't get any heads. And if Y is 0, it means we did not get a head on the first flip, which is going to be true. So that would correspond to the event tails, tails, right? This can help us think about what the corresponds to getting a tails, tails. X equals 0 means we have no heads. Y equals 0 also means we have no heads. So what's the probability of getting a tails, tails when you flip a fair coin twice? That is 1/4, right? 1/2 chance getting tails in the first times 1/2 chance getting tails in the second. What's the probability that X is equal to 1 and Y is equal to 0? Well, if Y is equal to 0, that means the first flip was the tails. If Y is equal to 0, the first flip is tails. And if X is equal to 1, that means you got at least one head, or you got exactly one head in the two flips. So the second one has to be heads, so tails, heads. Probability of getting a tail, heads, exactly in that order is also 1/4 as well. 1/2 chance for each of those. How about the probability that X is equal to 1 and Y is equal, to 1? Well, that would correspond to getting a heads in the first flip because Y is equal to 1. And then tails in the second because X is equal to 1. And let's just finish running through the combinations. We have both options when X is 0, both options when X is 1. Now we just need both options when X is 2. So we can look at when X is equal to 2 and Y is equal to 0. Now we can look at when X is equal to 2 and Y is equal to 1. If X is equal to 2, that means you have heads, heads. Y cannot be 0 there, so that intersection is empty, which means you have a 0 probability. And X equals 2, Y equals 1, is corresponding to heads, heads, which is another 1/4 probability. So we've gone through all possible combinations here of our random variables X and Y. We can summarize this information in a little bit more of a convenient fashion in a table, if you will, in a two-way table here. So let me just go ahead and do that. So let's see. we'll do something like this. 0, 1, and 2. So this can be, this will be x over here. And then what do we need? So y can be 0 or 1. So then this will be y here. And then we can put the probabilities. We could put the probabilities right in the middle here. So what do we have for 0, 0? That's a quarter. What do we have when x is 1 and y is 0? That is a quarter. X is 2 and y is 0. That's 0. How about 0, 1? That's 0. Filling this in. And then 1, 1 is a quarter. And 2, 1 is a quarter. All right. There we go. Now, what we have in our table here is really just the way we would express what's called the joint probability distribution. This gives us the joint values, the function f of x comma y, the multivariate function f of x, y. This is a joint probability distribution that gives you all the possible cases for x and y and all the probabilities. Anything that's not specifically specified here then is assumed to be 0, just like it is with a regular joint probability mass function. Okay, so with this in mind, as far as saying like what a joint probability distribution is, let's go ahead and take a look at the definition now of a joint probability distribution. All right. The function f x comma y is a joint probability distribution. Joint probability distribution of the, what do we have here? Of course, this is a discrete case that we've done so far. This is of the discrete random variables. We'll say x and y if let's see. So first of all, the function values are greater than or equal to 0 for all x and y. Of course, we're talking about probabilities here, right? So non-zero probabilities. Two. The probability that x is equal to some value little x and y takes on some value little y then should be equal to the function evaluated at that point. 3, if we add up all the probabilities, just like we did in the single variable case, all the probabilities should sum up to 1, right? So how do we notate adding up all of the probabilities here? It's not just a single sum. We don't just get to sum over all x, but we have to sum over all possible pairs. So we sum over all x, we cycle through that, and then for each of those, we add and cycle through y. This is a double sum, and make sure that adds up to 1. We make sure that adds up to 1. Okay? Make sure that adds up to 1. All right? And just like in the discrete case, if you want specific probabilities, not specific probabilities, but a range of possible values, you just add up all of the cases that fit that range. So the notation on this is we would say, so now that we have 2 random variables, your cases would be like a region in the xy plane. And so we say for any region, capital A, in the xy plane, the probability that you are a member of that region, you're in that region, is just the sum over all the values that are in that region of your function f of xy. Okay? There we go. We have that. So, real quick, I just want to tie this back into the last example. We'll take a look at this. Notice that when we sum all of our probabilities here, we add up the first row. We could take a look at this sort of, there's a total here, a quarter plus a quarter plus a quarter plus a quarter. In the last example, we have 1/4 plus 1/4 plus 1/4 plus 1/4. And we have some zeros in there as well, but that adds up to 1. That adds up to 1. All those probabilities do add up to 1. So we at least get to see that we satisfy that. And certainly, if we define our function based on these rules, we have nothing that is less than 0 for our probabilities. Okay. Good. So, nice. We have that. All right. That is in the discrete case. That is in the discrete case. I want to go ahead and just get through the definition in the continuous case at the moment. Definition 3.9 is for the continuous case. And it's very similar, except basically we replace our summation with integration in the continuous case, right? So we say f of xy is a joint density function, or a joint PDF, joint density function of the continuous random variables x and y if, well, as usual, f of xy is greater than or equal to 0 for all x and y, This is usually a little bit more interesting of a condition in the continuous case, right? Because frequently in the continuous case, you have some sort of algebraic rule that looks more like a traditional function there, rather than just a table specifying all the values. Where here, it's very easy just to specify that nothing is less than 0. But sometimes when you have a continuous density or a density probability density function, you're looking at things like, polynomial functions, for example, and you need to make sure that they're non-negative. The probability that x and y is in the region A is equal to the double integral over that region, f of x, y, dy, dx, or dx, dy, depending on how you prefer to do your order of integration. And of course, if we integrate from double integrate from minus infinity to infinity, integrate over the whole xy plane, we should get an double integral that evaluates to 1. Okay. Now, we have the joint density function of continuous random variables here. I have tried. I've set up the class. I am not going to be requiring any sort of double integration, because multivariate calculus is not a formal prerequisite for this class. Certainly, a lot of people, or some people, have had experience with that. Double integration is not too big of a step, but I am not requiring it. So if you do come across any problems that actually require double integration, let me know. Those are supposed to be omitted. All right. What is going to happen, though, is we are still going to work with joint density functions, because from these, without doing any sort of double integrations, we can get marginal densities, which will be functions of single variables and only require a single integration, okay? So we are going to come across these, but we shouldn't have to do any double integration directly. Where these are going to come into play for us is usually where something is a marginal, or we're going to use it to derive a marginal distribution. The marginal distributions of x, so x alone, and y alone, are marginal distributions would be taking a joint distribution and getting strictly a distribution for x alone and not getting the y, not including y as part of that distribution. So the marginal distribution of x alone, sometimes the notation here can vary. So sometimes I like to use f sub x to talk about the marginal distribution of x. The book oftentimes just uses the letter g for the function on the marginal distribution of x. How does one get the marginal distribution of x? What you do is you take your joint distribution, if we're in the discrete case, and you just sum over all the y values. And you reverse this process if you want the marginal with respect to y. And the book tends to use the letter h of y. Again, I like using f sub y, so I'll try to mix these in. H sub y, f sub y should be standard convention for us here to talk about marginal distributions. And you sum over all x values. You're going to sum over all x values if we're talking about the discrete case. In the continuous case, we can get these, the marginal distribution with respect to x, by simply integrating from minus infinity to infinity over all possible y values, okay? And so this is where we're going to see the joint density function show up, is we will probably be doing this integral. And we're going to have, even though it has two variables, we're only integrating with respect to one of those variables. And so we can handle that integral using our standard single variable calculus techniques. We just treat the other variable as a constant. We'll take a look at some examples in a bit on how we can do that. Right, so we do the integrals instead of the summation if they are continuous, okay? Marginal distributions, all right? Looks good. I think let's go ahead and just do one example. You know what? Let's pause there. That's enough for now. Let's take a break, and then we'll come back and we'll do a couple examples looking at maybe discrete joint distributions and continuous joint distributions and getting the marginal distributions. So we'll put these definitions in action, and maybe that'll help straighten some things out in a bit. So grab a snack, and we'll see you in the next video.